zone.
Good afternoon, I'm Daniel Steigerwald.
Sami, Awad.
Daniela, Chavez.
This is our project, Electrohydrodynamic Theory Applied to Flow Separation. Here's a brief overview of the topics we'll be covering during this presentation. So, flow separation is a major issue within the field of fluid mechanics. Flow separation is a boundary layer detachment of the fluid from the surface with which it is interacting. When boundary layer detachment occurs, it causes the fluid molecules near the surface to lose momentum. The momentum loss can cause issues such as increased drag in aerodynamic applications and decreased efficiency in turbine blades and rocket nozzles. So types of flow control that exist are active flow control and passive flow control. Active flow control can be switched on and off as needed, while passive has no switch. Therefore, active flow separation is the most efficient way to add momentum to the near wall flow. For this project, we are using active flow control using a nozzle and electrohydrodynamic theory, which couples volume body forces and electrostatic forces to add momentum to the fluid molecules. So the formulas we use in this project are the Navier-Stokes equation for the fluid forces, the Bernoulli's equation for the piping calculations, and the Maxwell stress tensor equation for the electrical forces coupled with the Navier-Stokes equation. So the overall objective of this project is to minimize flow separation within a converging diverging nozzle. The problems we encountered in this project are how to manage the flow separation, how to visualize the flow separation, how to minimize the time needed for the CFD analysis, and how to determine the voltage necessary to control the fluid flow. So our proposed solutions for those problems are to control the flow separation using electrohydrodynamic theory with electrodes, to use a planar nozzle that is not axis symmetric to better visualize the flow, to use a 2D flow analysis rather than 3D to minimize the time necessary for the complex CFD analysis, and to use salt water, the conductive fluid, to know the voltage necessary to control the flow. Here's an example, planar nozzle with electrodes applied. So a proposed experimental setup involves a tank running into a pump through a ball valve and then into our planar nozzle with a return piping system leading back into the tank to allow our setup to run continuously. And now Sami will talk about the simulations done for the piping system.
So after our proposed design, we went ahead and did the simulations. This is a simplification of our proposed design. This is the piping system. We first did the analysis to ensure that we have fully developed flow before the nozzle to ensure better results. Here's the analysis for the pressure and for the velocity. As you can see here, is fully developed flow. Here again is the analysis, velocity analysis in the diffuser. And as you can see, we achieve the same volume flow rate as coming into the system as the volume flow rate out of the system. And we got that the velocity before our nozzle, or the inlet of it, is 3.7 meters per second, which is close to our theoretically calculated. So then, based on these simulations, we selected the tank. The tank is a 75-gallon tank. It weighs, if you fill it to the top, is 304 kilograms. The pump selected can deliver the required 260 gallons per minute, and that will ensure that we get around 4.2 meters per second in the velocity coming into the nozzle. This pump is 2-speed, 230 volts, and 5 horsepower. Then we went ahead and did the simulations on the frame support for this tank after selecting the tank. As you can see, this is a steel angles welded together. This is the stress analysis. And the factor of safety was calculated based on how much you fill the tank. The more it weighs, we have to ensure that all the water levels are safe. And we found out that the minimum factor of safety for all of them was above 1. So it's safe to fill the tank to the top if needed. Now Daniela is going to talk to you about the nozzle simulation results.
So in order to find the dimensions, so we could see flow separation inside the nozzle, we use ANSYS, we use the turbulent model, and we use the simulations result obtained from the piping system simulations that require us to have an inlet velocity of 3.7 meters per second. So now here, you're able to see the flow separation from the upper wall of the divergent section of the nozzle and from the lower wall. Next, we plotted the error obtained from ANSYS. You can see that we have a 10 to the negative 7 order of error, which means that the software is simulating the flow behavior accurately. In order to validate the simulation, we perform the same, using the same input parameters, we perform the simulation using console, which means that we are using a different algorithm to simulate the turbulent model and the flow separation, and we got the same results. You can see here the error analysis. We have an order of error of less than 10 to the negative 3, around 10 to the negative 4, which is also acceptable. From these results, we were able to come up with our dimensions. We have a 6 inches inlet length and a 6 inches outlet length with a 2 inches throat nozzle. Note that this picture is not drawn to scale. Next, we proceeded to perform the simulations with the electrodes included. We have here 10,000 volts applied to the first electrodes here on the upper wall and minus 10,000 volts on the electrodes on the lower wall. Here you can see the simulation results, and you can see how flow reattachment is occurring at this region. Here you can see it better when you compare the no electrodes case, when you have flow detachment, with the electrode case, when you see the reattachment occurring on this area. This is for 10,000 volts. Next, we proceeded to place the electrodes at different positions inside the nozzle, and we alternated the polarity of the voltage. We are using 30,000 volts for this second case, and you can see the solution here, how we have greater reattachment on this region near to the upper wall. And here you can see how the flow is pulled upwards. Note that on this blue region, we have the flow being accelerated at 2 meters per second. This is comparing both cases, no electrodes with electrodes at 30,000 volts. You can see here the difference. Then, in order to make sure that our software was working correctly, we said that if we perform a velocity field difference between the velocity field obtained when electrodes were applied and the velocity field obtained when no electrodes were applied, we should get a positive velocity difference when reattachment occurs. So you can see here how we have of about 4.65% meters per second velocity difference when reattachment occurs. Here is our convergence graph. And you can see that we have an error of about 10 to the negative 4. So now, with these results, we proceeded to our manufacturing and prototyping. So now Sami is going to tell you more about that.
So our manufacturing was divided in 6 steps. The first step was actually welding the frame, putting the 2 pieces together, providing a middle support for the tank, then securing the pump with the hex bolts and making the electrical connections for it, just as you would with a standard household AC system. Then we proceeded to gluing the piping system, the suction side and delivery side of the pump. This will be the delivery side of the pump, and this will be the suction side from 1 inch brought to 2 inch into the pump. Then we 3D printed as you can see here, the diffuser and the reducer, and we coated them with black sealant to avoid leaks. Then we CNC'd the walls of the nozzle and glued them to the acrylic plates and bolted them to ensure that they withstand the pressure. Now, we had 2 options for power supplies. The first one we borrowed from the electrical department. It can give us 3,000 volts. And the next one we attempted to build, which is right in front of you, it gives you 30,000 volts. Here's the entire setup of our system. The tank itself, the pump right under it, the expansion, most importantly, the planar nozzle, and the reducer and the return piping system back to the tank. Now, after we performed the simulations and the manufacturing, we went ahead and wanted to validate our simulation results by doing the experimentation. Here you can see some the regions of flow separation. And here's a video portraying the flow separation when the pump and the whole system is running, as you can see here and here.
So next we proceeded to attempt to validate our flow reattachment by using electrodes. How did we do this? First, we study electrostatic attraction, which means that water is already a polar molecule, which means that it has high electronegativity, which means that it's going to be easily attracted to a strong electric field. And as you can see here, There is a video. We wrapped a PVC pipe and we are charging it with negative charge. And when you brought it close to the water gets attracted to it. So this is the basic concept that is behind the electrodes. So when we place them into the nozzle, we're expecting to see this similar behavior. Next, we also reason that if we have a high velocity flow, we're going to require higher voltage, and this is backed up by our simulation results. As Sami mentioned we had two options. We could use a 3,000 voltage power supply that was borrowed from school. However, we ran into some instrumentation issues. Our problems encountered was that we had damaged ground and high output voltage connections. We had unexpected overload, short circuit, and unexpected power shutdown, which would make our testing not safe. As a consequence, we decided to build our own 30,000 volts power supply. This works with a self-resonating circuit. However, we also ran into some issues. A self-resonating circuit is supposed to give you this type of signal, but we wouldn't be getting any, and this would mean that the power transistors that we're using are not resonating, and therefore they are not generating the frequency needed for the transformer to generate that high voltage. Due to time constraints, we proceeded to leave the power supply as is, and then we used the 3,000 volts for experimental trials, and that is going to explain more about it.
So we constructed the electrodes out of stranded wire with copper tape. We varied the electrode distance to see how it affects the stream of water, and we used a thin stream of low velocity water with the reasoning that the voltage necessary to control the flow would be lower than with a high velocity throughout the nozzle. We tested the voltage difference between the electrodes. However, the issues with the power supply persisted, and we had to find an alternative method to use the power supply. So we tested making electrodes, which use the power supply in a different way. Electrodes are a piece of dielectric material that hold a permanent electrostatic charge. So we used the power supply to charge the electrodes, and then tested it with a thin stream of water. However, due to budget and time constraints, we were not able to determine the actual charge that was placed in the electrodes or to implement them within the nozzle. So this is an overview of the costs incurred during the experimental trials and the manufacturing. You can see the total cost was around $1,700, with a bulk of it coming from the electrical equipment. This is due to the multiple trials that had to be run and the multiple parts for the electric components. However, without the additional experimental trials, the cost of the electrical equipment is much lower, and the total cost is closer to $1,300. The engineering standards we used were the ASME standard for the computational fluid dynamics and the ISO and IEC standards for electrical supply and electrical safety. So the system can be applied to any geometry of nozzle, and flow separation occurs in so many aerodynamic situations that our project is simply another part in the ongoing global conversation of flow separation control, along with the many publications from universities that we studied throughout this project. Additionally, we used both English and SI units to make our findings more applicable on a global scale.
So as a conclusion, we can say that we did manage to validate our simulation results for flow separation without electrodes by experimentations, as you saw before. Next, we were able to minimize flow separation by using simulations applying voltages between 10,000 and 30,000 volts. However, because of issues with the power supply, our experimental results are inconclusive. Next, we also were able to develop a methodology to test and manufacture electrodes. We have three necessary conditions that have to be followed. First, test for continuity, avoid sharp edges, and use stranded wire. Why? Because if you follow these three steps, you are making sure that you're going to have a uniform electric distribution across the surface of the electrode. Finally, this project is a really original project. Before, EHD theory has been used to external flow to minimize flow separation from airfoils, but this is the first time that we're trying to minimize flow separation inside the nozzle. For future work, we want to provide more simulations inside a Delaval nozzle. We also want to perform a multi-objective optimization in order to find the best position for the electrodes so we could have uniform reattachment of the flow. And we want to include the electrodes in the nozzle in order to validate our simulation results. Then we want to secure an AC power supply because we want to compare how much voltage are we going to need if we use an AC power supply. Maybe we're going to need less, which would be more beneficial for this project. And lastly, we want to share our findings in a poster. Here you can see the picture of our poster. Thank you, and we're open to any questions.
Got for your college resume.
Yes, any comments, questions, Fred?
Yeah, now the equipment you used, you borrowed from the electrical department, was giving you problems.
Yeah.
Yes.
So you put that aside and then you created your own machine,
We tried it.
We tried to make our own power supply.
okay?
This was done 1 week before the presentation.
Gotcha.
We had time limitations.
Right, I understand that. How'd you go about even start building your own, how'd you do the research on just getting to that point? What
You
did
start learning from scratch.
from
You
scratch?
start learning about self-resonating circuits and how generating the right frequency.
Uh-huh.
When it goes through the coil, when using a transformer, you can generate an AC behavior to then have a high output voltage.
I guess.
So-
Sorry.
So in order to be, I guess, more effective learning-wise, we went to the electrical department and we got help from one of the PhD candidates from one of the labs. He guided us to do the circuitry and he guided us on trying to debug the circuit so it could work. But we had the deadline for this presentation, time constraints, so we couldn't finish.
I'm sure that must have been the monkey
Yeah.
wrench thrown in the machinery in the sense, last second, oh, what do we do now?
Well,
Very
the
interesting.
other power supply was
Right.
already damaged. I mean, try to run your experiment with a damaged 3,000 volts power supply and try
Right.
connecting it to putting the electrodes inside the nozzle and running water through it.
Right.
Yeah, it could provide safety concern
Exactly.
when something could happen.
Because I'm seeing that and I'm like, that must have been
I mean, the first step
the
we
biggest
took,
challenge is that.
the first step we took into actually building that power supply is just trying to increase our voltage, turning it from AC, which is 120 volt AC outlet, converted to DC and actually boost it with a voltage tripler or Cockcroft voltage tripler, theoretically.
I mean, I was looking at that and said, oh, that must have thrown you guys for a loop.
Yeah, we learned how to do it from scratch.
Right.
Yeah.
Okay, yeah, just curious.
Did you actually need 30 kilowatt or 30 kilovolts to do that?
According to simulation results, yes. Well, we did in a total of 12 cases for simulation trials, starting from 1,000 volts, then going to 2,000 volts, then going to 3,000 volts. And I'm going to show you here. It's in there. You can. So this is the result when no electrodes are applied. When we use 1,000 volts, if you observe the picture, you're gonna get the same thing. And when we do the velocity difference, the change in velocity is barely here. So there is not a huge change. There is not gonna be any reattachment at all. So we started increasing 1,000 volts, 2,000 volts, 3,000 volts. It wasn't working. But since we have a 3,000 volts power supply, we said, okay, since this fluid is going between 3 meters per second, 11 meters per second at the throat, obviously we might require higher voltages, but if we use just water coming out of a syringe, we should be able to see some difference just by applying 3,000 volts. However, the power supply kept shutting down whenever we would try to even turn it on. It was unexpected. So there wasn't a way for us to actually say, oh, we see that.
Because at at 30,000 volts, I think you'd be vaporizing the water.
Yeah, but you can still run simulations for two-phase flow. For two-phase flows. Yes, we read about that. We can start vaporizing the water, but we will have now then to check what type of material we could use to manufacture the electrodes or what type of coating we could use, so we could have the real effect.
So your simulation indicates that when you apply high voltage, the flow gets attached to one side but detached from the other side. Does your simulation indicating, is it any possible that by applying voltage, the flow can be attached on both sides?
Yes, that will depend on where you place the electrodes. And that is why we mentioned that that should be left as future work, because that will require multi-objective optimization on where you're gonna position the electrodes. Like, this is just one case. We'll have to run different cases to see where is the best position for the electrodes so we can have a uniform reattachment of the water. And know that this is not the detachment. Here you don't have a zero velocity flow. You have a flow going at 2 meters per second.
Another question is, have you consulted with the electrical engineering students or faculty about the power requirement if you apply 30 kilovolts of voltage across the fluid? It may require large current and very high power.
It's actually very low current, just high voltage. I mean,
Right.
the system itself, if it's 5 milliamp, 30,000 volt, which is 90 watts,
Yeah,
like a light bulb.
I suspect that's why the power supply